Hi, my name's Carly McAvoy, and I'm going to be doing the Statistics 6A homework assignment today. So let's take a look at it. I think I'm going to do most of it on paper, as I usually do, but I'm going to open it up just for the heck of it and see what it looks like. And I do that sometimes so that if there's something I need to enter, I'm not really sure what they're going to ask of you, so I want to enter it myself just to kind of see. That's kind of a pain, but anyways. This first one that we can do on this screen. What requirements are necessary for a normal probability distribution to be standard normal probability distribution? They standardize it, it makes it easy to work with. So they make the mean 0, so the middle of your bell curve is 0, and they make the standard deviation 1. That just makes it easier to work with. So let's see where they have that. The mean should be 0 and the standard deviation is 1 right here at C. That's what standardized. When they standardize it, that's what they're talking about. Okay, find the area of the shaded region. The graph depicts the standard normal distribution with mean 0 and standard deviation 1. Okay, so I'm going to switch over to the paper because I want to talk about this. But they always have this thing, and you can do it with a table. You are going to do it with your calculator. So once you understand, well, it's easy to do it on your calculator anyway, but it's nice to understand what you're doing. Okay, so we want to go for more than just what the calculator says. But let's switch over to my paper and we'll do these there so I can show you a little bit more about that. Okay, so that was one. Number 2. Okay. So find the area of the shaded region, and the graph depicts the standard normal distribution. So we know that the mean is 0, that the mean is in the middle of your standard distribution, so right there, and then the standard deviation is 1. Remember, your z-score is like your standard deviation, except that there's a sign on it. So if it's a positive z-score, it's to the right. You can tell if it's 0.45, that means it's just slightly less than 1 standard deviation to the right of the mean. So of course our point is right here. And remember that the entire curve, this whole area under the curve, adds up to 1. So what this is saying is our z-score is 0.45. How much of that area is in this shaded area? That's what they're asking about. So we want to know the area, and we don't know it. We know the z-score though, and we know, what would we know? Would it be less than half or greater than half? Well, if I had a z-score of 0, that is, I was right here at the mean, that would be half. And so a mean of half, a z-score of half gives us 50% or 0.5 of our whole 1. This one covers all that half plus a little more. So when I find this, I would expect my answer to be a little more than 0.5 because it's more than half shaded, right? So if you get an answer of 0.23, that shouldn't make sense to you. So I want you to understand the whole thing is 1, and we're looking for the area of that one thing. And we're going to do on our calculator Normal Cdf. And then you go through and you put in the information. That is, they ask you, what's the furthest to the left? Well, on the left of our picture goes forever to the left. So we do, well, let's look at it on the calculator, and then that makes, so I won't say something that the calculator looks different. So I'm going to do second function data, and I'm going to do distribution, go to the right, and I'm just going to go down to Normal Cdf. That's the second one on there, and hit enter. And it asks me, what is your mean? If this is a standard normal distribution, our mean is always 0, so that's good. And our standard deviation, or sigma, is 1. And then it's asking you, what's your lower bound? And I was just getting ready to say that. On the left, it goes to negative infinity, right? If I went over here, it would go negative infinity. And on the right, it'd be positive infinity. So our lower on our picture is going to the left. So we want negative infinity, but the way the calculator is going to enter that is -1 e to the 99th power. In other words, here's our decimal. We're going to move our decimal 99 places to the left. And 99 places to the left means 99 98 zeros and a 1. It's pretty close to negative infinity. They just do that because it's so close to the same, it doesn't matter. And if it was going to the right, we would do 1e to the 99. But anyway, ours is to the left. And then to the right, we're stopping at that point that they gave it, which is 0.45. So our left is negative infinity and our right is 0.45. That's where we went. So here we go. On the lower bound, it already has in there set up to go negative e to the 99. So that's right. But on my right, I want to hit clear, and then I'm going to put 0.45 because that's where I'm stopping as I go to the right. I'm not going all the way to the right. What would I get if I just left it as it was? Well, we can see that in a second, but it should be 1, right? Because okay, I'm going off on a tangent. Let me stop that. If I go from negative infinity up to 0.45, what I'm getting is 0.6736. That's the percent out of 1, or the part out of 1 that's shaded in that diagram. So about 67% is to the left, and then the rest of it to the right is unshaded. So that's what I put in there to get that. All right, what I was saying before, if we did that normal distribution and we just left it in there, 0 and 1, and said negative infinity to positive infinity, that's covering the whole thing. And if I cover the whole thing, I should get 1 because I did, because it's 1 is the total covered, right? So I'm always looking for some part of that. So 0.6736. I don't know where that answer went. This thing got all messed up. It doesn't matter. Okay. Now I'm looking at the same kind of thing. I have a mean of 0, standard deviation of 1. Now I'm starting at negative 1.07 and I'm heading over here to infinity. And remember, infinity is going to be 1 e to the 99th on your calculator. So I'm going to put that in there. I'm going to do solve again. No, I don't want to do solve again. Let me show you what happens if I do solve again. If I do solve again, it keeps your last values. Oh, well, I used that. No. Like my last values, I didn't change anything, so it doesn't show you anything. But anyway, as I go in here now, my lower bound, or the lower number, is negative 1.07. But the upper bound is infinity, so I don't want to change that one. And that gives me 0.8577 rounded to the 4th decimal places. Okay, so let me see if I just say solve again and go in there. I just wanted to show you what happens. It automatically leaves that in there, and then you have to go in and put the negative, like negative infinity would be negative 1 e to the 99th. So it's kind of a pain, a little bit of a pain to do that. So you might just want to quit out of it every time instead of just solve again. Okay. Now I'm going to go look at this one down here where I have a range of values given. It's a standard deviation. I'm going to use normal CDF again, but instead of going to infinity on either side, I'm just starting here and ending there. So I go to second function distribution, second function data, then distribution, then down to normal CDF, and then I put in those values. Well, I've got a 0 and a 1 there, and then I have on the lower bound, I have negative 0.94, and on the upper bound, I have positive 1.24. Those are just the two numbers that are given there. I give the range of what I'm looking for, and I want to know how much is the shaded area in there. And it's pretty easy because it just gives me that answer, 0.7189. I kind of love these. They're kind of fun, but you really have to think about, are you going left, are you going right? Now we're going opposite here. You see how here we had the z and we wanted to know what the area was? Now they're going to start giving us the area and asking us what the z-score is. I have to pause for a second to get my light back on because it bugs me to do this in the dark, and I wasn't active enough to keep my lights on. So anyway, so this is when you want to say, obviously you can't do the same thing. You're asking for a z-score, and before they were asking for the area. Now they're giving us the area, asking for a z. Still easy peasy on the calculator, but you have to remember when you already have the area, you need to use inverse normal because we're doing the inverse of what we just said. So we're looking at that inverse normal function on the calculator. Second function, distribution, and then if you go down to number 3, it says inverse normal. Now it tells you, it asks you, what's the area? Well, they gave us the area. It's 0.8461. And we still have a standard distribution. If it has a standard distribution, we have a mean of 0. We have a standard deviation of 1. So all I have to do is make sure that my mu is 0 and my sigma is 1. And then calculate. And what that gives me is a z-score. And you can see that if I had a z-score of 0, I'd be right down here at the middle. That'd be a z equals 0, right? But obviously my z-score should be more than 0 because it's to the right. And it turns out to be 1.0, what do they want to 2 places? Yeah, 1.02 is my z-score. You can see that that makes sense. It's to the right of that middle point, so it should be positive. And it's not hugely over to the right, so 1.02 makes sense. So that would be that to the second decimal place. Okay, find the indicated z-score. Again, you're finding a z-score and you're given an area. This area right here, this shaded area is 0.7123. Second data, distribution, down to inverse normal. Then I just put in what I know. I know my area is 0.7123. And I have a mean of 0 and a standard deviation of 1. We don't always have that. If it's not standardized, we don't, but we do now, so I don't have to worry about it. So enter, and I get 0.5601. Now, here's where I want to be careful and why I want you to look at the picture. Here's where my mean is. That would be a z-score of 0, right? My z is to the left of that. But when I put that into the calculator, it gave me 0.56. 0.56 would be to the right of that, right? So what's happening? Well, your calculator, when you're doing inverse normal, it always assumes that you're interested in what's to the left of that. So they're always assuming it's to the left. So I'm not going to get the answer of positive 0.56, I'm going to get the answer of negative. So that's when it helps to actually look at that and go, wait, should my z-score be positive or negative? It's just the way the calculator does it. It's the way the standardized tables do it as well. They always assume that you're looking at the area on the left. So the area on the left is this area over here. We were looking to the right. It gave us the number, but it gave us the number in its opposite form. So that's something to remember. I gotta change that, and it should make sense that it's negative because it's on the left side of 0. So it's negative 0.56. Okay. Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed, mean of 0, standard deviation of 1. Find the probability that a given score is less than 1.02 and draw a sketch of the region. Well, less than 1.02, or sorry, negative 1.02. Here's a negative 1.02, and it's everything less than that. This is a negative 1.02, everything to the right of that, and this one's a positive, and this one's just bizarro. So we know it's this one. And then we need to know, well, if I know the z-score, and I'm trying to find the area, which one do I use? Up here I knew the area, so I use inverse normal. But down here, I want to find the probability. So I'm going to use normal CDF. So you have to get that straight. Put it in your notes. If you're given the area, you're going to use inverse normal. If you're given the z-score and want to find the area, which is the probability, then you need to find the normal CDF. And so we're looking at second function data, distribution, normal CDF. They told us that we had 0 and 1, so that's all good. And on this one, we're going to the left forever, so we have the negative for our lower bound. And our upper bound is the negative 1.02. It's important that you put that in the right place, otherwise you get a different answer, right? So we have B, which was our picture, and C, 0.1539, rounded to 4 decimal places. All right, so assume the readings are on a thermometer are normally distributed with a mean of 0 and a standard deviation of 1. Find the probability that a randomly selected thermometer reads greater than negative 0.077 and draw a sketch. Well, Negative 0.77 are on both of these, and we want greater than. Since it's greater than, it should be to the right, so it's got to be this picture here. And then we want to find that. Well, we know the z-score. We want to find the probability. That's a normal CDF problem. We know the z-score, then it's normal. So I'm going to do second function quit, second function data distribution. Some of that's probably, I probably just could have done second function data and instead of quitting and whatever. You'll be faster and better with your calculator. You're probably younger and just better with technology in general. Okay, so normal CDF, we got a 0 and a 1. We're all good on that. We're going not forever to the left. We're starting at the left at negative 0.77. And we're going forever to infinity. And so that gives us the rounded place of 0.7794, rounded to 4 decimal places. Aren't these kind of fun and easy? Okay, assume that these thermometers are normal, 0 and 1. A thermometer is randomly selected and tested. For the case below, draw a sketch and find the probability that the reading is between 0.25 and 1.25. Well, the only one they show up here that's between two values is right here, between 0.25 and 1.25. We are looking for a probability, and so that's a normal CDF. If we have the probability, then it's inverse. All right, let's see if we can shorten this. Second data, yeah, that's all you had to do. Then you go down to normal CDF, and you say I have got 0 and 1, and my left one is 0.25, and my right one is 1.25, and so when I calculate that, I get 2957. Right? All right, I bet you're cruising through these along there with me. Okay, assume that the readings on a thermometer are normally distributed with a mean of 0, standard deviation of 1. Assume 3.3% of the thermometers are rejected because they have readings that are too high, and another 3.3% are rejected because they have readings that are too low. Draw a sketch and find the two readings that are cutoff values separating the rejected thermometers from the others. Okay, we have some on the end that are being rejected and some on the because they're too low, and some on the end that are being rejected because they're too high. So it makes sense that we have this picture because some on the left and some on the right. This just has one tail. These are kind of called two tails. And this has just a middle point. This has one tail. So it's got to be A that we're looking for. Now the cutoff values are how many degrees. So what are we given here? Are we given the percentage or are we given the z-score? Well, we're given the percentage. Even though they gave it this way, we can think of it as move it over 2 places. And what do I know? I know that that's 0.033. I also know that this area is 0.033. So I can find those two because I'm going to use inverse normal. Right? And if I use inverse normal for one of them, I'm going to clear. I can always clear an area or something just so I don't make sure I don't end up with something left over from before. If I do 0.033 and hit enter, it's going to assume I'm interested in what's to the left. And what's to the left is negative, the z-score that would be to the left of that is negative 0.84. 1.84, I didn't say that. But I don't need to do that again because the same thing would be happening to the right. It's the same z-score, only it's positive instead of negative, right? So we have a negative 1.84 and positive 1.84 on that one using inverse normal. Okay. The area of the shaded region, find the area of the shaded region. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100. Something's new here. We don't have a mean of 0, and a standard deviation of 15. So when I put that into my calculator, I need to do that instead of 0 and 1. But when I want to find the area, I'm still going to use normal CDF. And I'm going to say it's everything to the left of that, which is going to negative infinity, which we always call negative 1 e to the 99th on our calculator. So this is the left and this is the right. So let's go in and do that. Going over to distribution and going down to number 3. You can just hit 3 on your calculator. You can scroll down to 3. It doesn't matter. Okay, we don't know what am I doing inverse normal? We want normal CDF. I can just go to number 2 for that case, and it'll just take me right in there. My mean is 100. My sigma is 15. They gave me that in the problem. And then my bounds, well, I want to go forever to the left, so I'm going to leave that one. But on the top, I want to go to 125. And now I'm going to calculate that. And that's going to give me a value of, remember, this is 0. And so I would expect my z-score to be to the right. And it turns out that the z-score, and this is probably to 2 places. Oh, they want the area. Sorry, that's what I'm finding. That was a little slip up, sorry. The area of this, not the z-score. We already know that this is not the z-score, but we could convert it to a z-score if we wanted. But anyway, it's 0.9522, 95%. That looks like about 95% of that, so it makes sense to me. 0.9522 is the area for that. Now, if you go in here again, well, here they give us the same thing. They tell us that mu is 100 and the standard deviation is 15, and they want to know what are what's percentage in this range. But I just want to warn you that if you do this, let's say you went in, the next one they told you that the mean was 75 or something. Well, when you go in there, unless you clear out your data, it's going to leave in there the data that you last entered. So you see how this is 115? And that can mess you up if you don't check it, because it doesn't revert back to 0 and 1 unless you do this. Unless you do on, clear, clear, and memory is cleared. Then when you go into data, it automatically assumes that you're talking about 0 and 1. So just be careful that you don't leave your data in there from previous sets, right? But anyway, this one is between 100 is the mean, and the sigma is 15. And the area is not between infinity and negative infinity. It's between 104 and 128. And when I calculate that for an area, I get 0.3639. Okay, so there that is. All right, find the indicated z-score. You know, you are seeing some of these things I'm doing over and over. If you've got it, then pause and see if you can do it. So now we have again the mean of 100 and the standard deviation of 15, and they're saying find the indicated IQ score. So they want to know what number should go here. So in this case, we need to use inverse normal because they gave us the percentage. So we have to use inverse normal for this one. Second function data, distribution, we're going down to inverse normal. Notice that they still have in there 115, which is good for us because it's the same, but you want to make sure that it always matches your problem. We have 0.65 for the area. And so in that case, our not our z-score, but our IQ score at that point would be, how far are they to 1 decimal place? 105.8 would be where we would round that for that one. All right. Find the indicated IQ score. Again, we have a mu of 100. We have a standard deviation of 15. And our area we're going to put into there is 0.97. What would you use here? Inverse normal or normal CDF? If you're given a percent, you use inverse normal. So distribution, inverse normal, and we have 0.97, 115, and we can find our score of if they were in the middle. So I'm seeing, okay, this is good because I kind of was like rushing through, haha, I got this stuff, right? But then I go, whoa, wait a second. If they were right here in the middle, we would expect a score of 100. So if they're over here to the left of that, would we expect a score of 128? Not really. We would expect a 128 if it was on this side. But what did I tell you about the calculator? It always assumes you're talking about the left side of that, right? So I need to figure out what this little area is because I want to know what's to the left of that. And all I have to do is take 1 minus 0.97, and that's going to say, well, all this was 0.97. 1 minus that is what's on the left of it, which is 0.03. So I need to put in 0.03 for my area because that's the area that's to the left. Remember, the calculator always thinks you're going to the left. And if you forget that, but you understand what's happening here, you're going to see a red flag like, whoa, how could I get 128 when the average in the center is 100 and I'm way to the left of that? Doesn't make any sense. It's good to have common sense. Even if you try to rush a little on your homework, your common sense should slow you down. Okay, 0.03 for the area. We got 100 and we got 15. And if I hit calculate that, I get x equals 71.8. That makes sense. 71 is less than 100. That starts to make sense, right? All right. Assume that adults have IQ scores that are normally distributed with the 100. Maybe that's actually a true value. They keep using those same ones over and over. I don't know. Find the probability that a randomly selected adult has an IQ between 81 and 119. Draw the picture. It's really useful to draw a picture and see what you're talking about. So if my mean in the middle is 100, that's what the middle average is, then what would it be between 81 and 119? I'm looking for this area right in here. And if I want to find an area, I use Normal Cdf. So second function data, distribution, Normal Cdf. I've got 115 working for me, so I'm going to leave that in there. I don't have a negative infinity, positive infinity. I have a lower bound of 81 and an upper bound of 119. And so the area in here is this is supposed to be to 4 decimal places. 0.7947 to 4 decimal places. My light's kicked off again. I think I'm just going to deal with it. Okay. Assume that they have a mean of 100 and a standard deviation this time of 20. Find P of 15, which is the IQ score separating the bottom 15% from the top 85%. The 15th percentile means that if you were in the 15th percentile, that's kind of a little sad because it means that you had 85% of the people did better than you, and you did better than 15% of the people. Not really sad, but I'm just saying, you know. So this is what we want to find, the area over here. If the area is 0.15, I mean, what's that score that you would have gotten there? So in this case, what they gave us was the area. So we're going to use inverse normal. Second function data down to 3. And our area is 0.15. Our mean is 100, but our standard deviation in this problem is 20. So we get 79.2, oops, I should lay that down, 79.27. I think they wanted that to, I've written down 79.20. To the nearest hundredths. Well, I get that. I get 79.27. I'm standing by that. I wrote that down from some other day. I don't know what I did, but 79.27 to the hundredths. That would be the score that would put you at the 15th percentile. Okay. Percentile is written like that. If I talked about the 60th percentile, then I'd be saying what score would separate the bottom 60 from the top 40. It's just a way of separating those things that way. So that's all that is. Okay. All right. A survey found that women heights were normally distributed with a mean, I'm going to write this down, mean of 63.4 and a standard deviation of 2.5. Those are inches. A branch of the military requires women heights to be between 58 and 80. Find the percentage of women meeting the height requirement. Are many women being denied the opportunity to join the branch of the military because they are too short or too tall? So we are looking for the area that is between 58 inches and 80 inches. 58 inches. Okay, so if you're 5 foot tall, it's, you know, it's 60 inches, so there could be 410 all the way up. So yeah, it doesn't look like too many people being denied, but I'm just, this drawing may not be that accurate. Maybe it should be that the lines are way further out, because it looks like a lot of high percentage of them are going to meet that. But we're looking for the percent, and we know our stuff that we want to put in here. So I'm going to just clear out my data because I've switched to new mu and stuff, so I don't want to mess that up. So I'm going to go to, I want the percent, so I'm going to go to Normal Cdf. My mean is 63.4. Standard deviation is 2.5. The lower bound is 58, and the upper bound is 80. Okay, and then I hit enter that. 0.9846 to 2 decimal places. Well, that's 1 after that. If I move this over 2 places, 98.46% of the women are being allowed in. So find the I didn't write down the answer to that earlier, but anyways, the answer, second part, is D. Are people being denied because they're too short? No, only a small percentage of women are not allowed to join. Most are. Less than 2% are sent away. For the new height requirements, this branch of the military requires women's heights to be at least blank or blank. What's the new part say? If this branch of the military changes the height requirement so that all women are eligible except the shortest 1% and the tallest 2%, what are the new height requirements? So that looks like this. We now have 1% or 0.01 over here and 2% or 0.02 over here that we're not letting in. And so we know we still have a mean of 63.4 and a standard deviation of 2.5. Here we were looking for the percentage, so we used Normal Cdf. Here we are looking for we have the percentage and we're looking for that score down here, so we would say inverse normal. We're going to do it twice because we have 2 different values, right? So we're going to, for the first one, the calculator is going to assume that we're looking to the left. So that's good because we are. So we're going to go to distribution, inverse normal. The area is 0.01, and our information 63.4 and 2.5 is already in there, so that's good. And so I can just calculate that. And I get 57.6, which is right here, rounded to the tenths. Now be careful on the second half, because on the second half, if I put in 0.02, it's going to assume that I was over here at 0.02 and looking at everything to the left of 0.02. They don't know you really don't mean, you mean 0.02 on the other end unless you tell it. So you're going to say, I'm actually looking for 1 minus 0.02 or 0.98, because to the left of this thing, if 0.02 is on the right, then 0.98 is over here on the left, right? So that's what I need to put in for my inverse normal. So just remember, the calculator thinks to the left, and you need to let it know what to the left would actually be. 0.98 to the left. And that gives me 68.5 when I put that into the calculator that way. So the new requirements would be 57.6 up to 68.5 if they changed it to the excluding only the 1% on the bottom and the 2% on the top. I just know somebody recently who wanted in the military. Actually, he lives in Italy, but he wanted in the military like all of his life. That's all he wanted to do. And when he got in, when he went to apply, he did all kinds of extra stuff to make sure he'd get into this military academy. And when he got there, they rejected him because he was half an inch too short. Think about that. Anyways. All right, the length of pregnancies are normally distributed with a mean of 267 and a standard deviation of 15 days. Find the probability of a pregnancy lasting 308 days or longer. So that means that we're looking at the area. Here's 267. Here's 308 over here. And we want to know the probability of it lasting longer than that. So we want to know what's the area over here more than 308 days, right? Well, we want to know probability, so we're going to use normal CDF. I'm changing my mu and my standard deviation completely here, so I'm going to clear out by going on clear, clear. I don't want to deal with having the wrong stuff in there. So I go down to my normal CDF. My mean now is 267 and my standard deviation is 15. Now I'm talking about from 308 lower bound to infinity, so that's already in there for me, and I just hit enter. And that gives me, I keep moving my calculator around, sorry, 0.003. I didn't put the answer to that here, but this 0.003, which is a really small percent of the people that would have that, right? That'd be over 10 months, right? So not many people doing that. All right, maybe your baby is part elephant if that's happening. Okay, babies who were born on or before what days are considered premature? If the length of pregnancy in the lowest 4%, so let's look at that, the second part, B, lowest 4%, well, I shouldn't be flipping that up at the end like that. Okay, down here, our lowest 4% is 0.04. Then the baby is premature. So we want to know how many days would it be for us to consider that baby to be premature? Since we were given the percentage, then we want to use inverse normal. Second data, distribution down to inverse normal. The area is 0.04. Our mean and our standard deviation stayed the same because it's the same problem. So I hit enter and I get 240.7. So to the nearest day, if that baby is 241 days or less, then it's considered premature. All right, that is the end of that. Whoa, I flipped out of there pretty quick. Let's flip back to this so I can shut it down, and I will see you next time.